Hello everyone, welcome to this video. My name is Sentinel-3. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to work with Sentinel-3 OLCI images to produce cloud-free NDVI data using maximum value composite algorithm with monthly temporal frequency. The data are free of charge and globally covered, and you can use this product for all around the world. So let's go to the code editor environment. In the JavaScript platform code editor environment, in the first step, we need to identify the region of the interest. Through the search places dataset, you can call different shapefile layers according to the border administrative layers or based on the basin you are working. For example, I'm working on a basin in Iran, and also here I'm gonna find the appropriate shapefile for. Through the search places and dataset, just type hydroshed layers. The hydroshed is one of the most important products in the hydrology that provided various hydrological products in the geospatial data analysis. And one of the most famous one is hydroshed basin levels. As you can see, it's available in different levels, and one of the mid levels is basin level number 5 that I'm gonna use that for this tutorial. So these basins layers covered globally, and also you can find your appropriate basin based on the global coverage. So here, for example, through the map.add layer, I can show you the global coverage for the table layer. As you can see, all basins available in level number 5, you can see is available, and my target region of interest, my target area or the region of the interest is a basin in the northwest of Iran, including Urmia Lake and also some croplands here. So if you wanted to clip the hydroshed border or the basin border according to your study area, it's very simple technique. Just you need to mark your basin first, and then through the filter bond we can clip our region of interest and separate it from the other basins available here. As you can see here, I'm making a new variable as a region of interest or ROI equals to from table or input table filter bond. I'm filtering based on that filter bonds. I'm filtering based on the geometry or mark region that I have selected. This is the geometry, and then through the map.add layer I can show you the region of the interest that is clipped or filtered based on the geometry we defined. So for the next step, I need to have focus on the study area when the code runs. To do this, map.centerObject is a helpful function. As you can see, map.centerObject ROI helping me to have focus on the study area when the code is running. And another thing that will have impact on the speed of processing in the code editor environment or Google Earth Engine platform is the complexity in the shape of the borders or shape files. So to reduce the complexity in the borders or to reduce the number of vertex in the shape, you need to use simplify function in the Earth Engine that highly help you to improve the speed of processing. As you can see, after filter bonds, as this is a feature collection, we need to make a function just like that. For input feature that is selected region, we need to apply the simplify function. Just function returning the feature, the input region, the input feature that is simplified according to the number or the maximum error that we can define easily from 0 to unlimited value. For example, here I'm set the 1000, and after the code runs, you can see that the a highly complexity reduced in the output. And even if I increase then actually the degree of simplification, finally you will see that the final border is simplified based on, get more simplified based on. That's what it looks like. So back to the previous degree value, because I want to do the simplification in a manner to keep the main border same as the original data with lower number of vertex. So then for the next step we need to make a variable including Sentinel-3 data. Make a new variable, a new variable as Sentinel-3 equals, here we have a tab search for the satellite or shapefile data available in the Earth Engine data catalog. As we talked about that previously, here you can write the name of your desired satellite or product, and after listed here you can pick and import it into the code. So now in their search places and dataset, write to Sentinel-3, waiting to see the response. As you can see, Sentinel-3 OLCI image that is available and usable for the ocean and land color studies, or OLCI means ocean and land color instrument. So import it into the code as an image collection. Then assign the image collection to the Sentinel-3. So now we need filter date and filter bound for the region of interest. Through the .filter date, you can set a period of time in which Sentinel-3 data is available. If you need to know since when this data is available, go to the data description, and here in the dataset availability that mentioned the data is available since 2016 or 2017, because it is related to the 2016 October, but October 2016, and also would be better to call the data since 2017. And the collection snippet and the information available here, and the spatial resolution for this data is 300 meter spatial resolution with every roughly 2 days temporal resolution. Sometimes in some regions it is daily, and sometimes in some regions it is every 2 days. It depends on different locations and also a different region of the interest you are working. If you go to the bands description, you can see that various bands available from the satellite sensor in the visible and near infrared region of electromagnetic spectrum, band number 1 to band number 21. These are the radiance images. The radiance means the electromagnetic radiation received by the sensor, and including the emissions and the reflectances values from the surface, Earth's surface, and affected by the atmosphere, and then received by the satellite sensor. And as you can see, the application and also the usage of each band explained well in the description, and based on the wavelengths, you can see that these data available for the visible and also the near infrared region of electromagnetic spectrum that make it a unique satellite data for the vegetation and water studies. And as you can see, it has various applications regarding to the vegetation, land, and also the water quality and the water studies. In this tutorial, I'm going to show you an example of application this product in the vegetation cover studies that could be very useful for you. So back to the programming environment. So according to the filter date and based on the dataset availability, I'm gonna set a period of time through the time start and time end. So here make two new variable, time start equals to, for example, I'm gonna call 3 years data here from 2020 to 2024. Time start and time end. Time end equals to 2024. So, and for the next step, we need to bound our data according to the region of the interest we are working. Dot filter bound, bounding the data in the region that's already identified as an ROI. So if the code is a little small, I can increase the size of codes and also the size of scripts to be visible for the users easier. So for the next step, we need to call the bands for each date and calculate the NDVI. As you can see in the data description, we don't have any NDVI bands that already existed in the band or in the data set for each date. So we need to find the appropriate red and near infrared band first, and then calculate the NDVI based on the band's information. As you can see, for the near infrared region, the 800 nanometer could be a useful part for the vegetation studies. So band number 17, as you can see in 865 nanometer, is a good choice for the near infrared option as a near infrared band for the vegetation studies. And also in the red region, so the band number 8 in 600 nanometer could be useful to study the chlorophyll and also the vegetation. So based on normalization between band number 17 and band number 8, I can calculate the NDVI for each date separately. So there is a scale factor here that helping us to apply on each available band to calculate or to ranges our data between 0 and 1. To ranges the input data into the actually standard range value for the radiance bands. But as it is as there is a linear relationship between the original value and the radiance value in this product, for some calculations such as NDVI, you don't need necessarily apply the scale value on input images, because there is a linear relationship between the original values and also the radiance value in this product. So back to the code, and then through the map we need make a loop, or we are going to make a loop to call each input images into the loop and calculate the NDVI for each band. So each input image in the function called as an IMG inside the parentheses or in the function body, make a new variable as NDVI, just like that. From each input image that's already named as an IMG, that normalized difference helping us to calculate the normalized relationship between band number 17 and band number 8. So the radiance for near infrared region, band number 17, and the radiance for band number 8, as you can see here, copy and paste it. After NDVI calculated, rename it to the NDVI band. So the function returning the NDVI value for each date, and also we need the input properties, specifically system time start and system time end, for the further processing in the next step. as we need to do the time series analysis in the Earth Engine platform, it is necessary to have the date acquisition information or acquisition date information on each band on each image as a single property. System time start and system time end, just like that. So now the NDVI value for each date calculated. In the next step, we need to convert this data from the daily resolution to the monthly for the 3 years we are working. So as you can see, I can print some of the images that is calculated so far and to have a preview about the condition of estimations so far. So make a print Sentinel-3, run the code. In the right panel showed there is a problem in the NDVI calculations. So the line number 15, as you can see mentioned, there are too many arguments. So let's see what's the problem. NDVI equals from each input image dot normalized difference. I think we need to use brackets here to solve the problem. Yes, the problem is solved. The input bands must be included into actually the bracket. So here 2362 NDVI image calculated for each date. In each date we have a single band as an NDVI, and also the system time start and system time end also available or attached to each image as a metadata information for the further analysis. If you want to have a visual preview about the output, it's very simple to use map.addLayer. The map.addLayer is one of the popular functions in the Earth Engine platform, allowing us to visualize our estimations very well and easily and with a useful manner. So the Sentinel-3, for example, I'm gonna make a median image for the whole period of time I have calculated, and then for the visualization, clip it based on the region of the interest and leave the visualization parameters empty, and the layer name is Sentinel-3 preview, NDVI preview, and then use the false at the end. The false here allowing us to stop automatic visualization. So that's helping us to increase the speed of processing, because while the code is processing, if you actually don't use false here and the outputs automatically show in the map, in the Google map you have here, while the code is running, that highly reduces the speed of processing. That's why we need to control the visualization process in our estimations. Save the code and then run it based on. You can hide the marked region to have a better preview, and then click on the Sentinel-3 preview. I'm waiting to see the result. As more than 2000 images involved in the processing for the median estimation to make a single image, meaning that we have a heavy data set and processing that is doing by the Earth Engine servers. That's why visualization of such heavy data takes a little time in the processing. So after a few seconds, you will see the final result. For now, we have to wait to see the result. If you cannot see the result or taking longer than expected, you can get an instant export from the layer that is created and check the output into the desktop software you are working. For example, export.image to drive helping us to get export from the median image. Export.image to drive. As you can see, the main image is Sentinel-3 median, or the median image that is clipped based on the region of interest. As you can see, the map is visualizing now, but we can do the programming steps and try to save the result in the Google Drive and also check it out in the desktop softwares such as QGIS. Another argument is description refers to the name of the output, Sentinel-3 output. And then a scale of processing. A scale of final image is 300 meter because the spatial resolution is 300 meter. But if you want to speed up processing, you can reduce it to 1000 or 1 kilometer. So, and then the region of interest, RO equals to the ROI. The maximum pixel allows to have allows in each actually the maximum pixel we can have in each raster tile equals to 1E13, and then the CRS, the coordinate system, equals to WGS84. So it is EPSG 4326. So as you can see the final output visually, you can increase the contrast through the enhancement techniques available here. But if it is still a time-consuming process, I suggest you to save the code again and run it to get export from the preview image and open it up in the desktop softwares. In the task, as you can see, we have a new output or new data that is ready to get out to output. Click on the run and again run. Now we are waiting until the final result saved completely and turn to the blue color, same as the previous tries, and then we can pick it up from the Google Drive that is connected to our Gmail account and Google Earth Engine account. So here in the console, we have an error about the invalid storage type, meaning that this data is too heavy for the visualization, and sometimes we may face with such kind of problems or errors during the processing. But it doesn't, and also, but you should remember that such kind of errors not related to the type of processing or scripting you are doing. It's directly related to the volume of the data you are processing. So in the task, as you can see, the data is saving into the Google Drive, and same time we can continue our scripting, and once the results gets ready, I will visualize it in the QGIS for you. Back to the programming steps, and also we had a quick preview from the outputs previously. So in the next step, as you can see, previously the NDVI calculated, and now I'm gonna convert the NDVI values to the monthly format. So how to do it? Make a new variable. For example, here I need a list for the, for example, I need a list for the number of years and the number of months I need to get export. So here the months equals to Earth engine dot list dot sequence. The Earth engine list dot sequence is a function that helping us to make a list according to the start and end value. So as we have 12 months per year, here the start is 1, the end should be 12 because we have 12 months and we need a list with 12 records from number 1 to number 12. So use the prints to see what the variable includes. As you can see here, we have a single list starting from 1 to number 12. So next we need another variable or we need another list of sequence for the years of study starting from 2020 to 2024, but remember that the only 2000, 2020, 21 and 23 included in the processing. So make a new variable as years equals to Earth engine dot list dot sequence. The start should be equalized to time start equals to time start and the end equals to time end. Print the years, print years. Once the code is running, you will face with an error. Invalid argument specified for Earth engine.number. As you can see, the start date and end date are in string format, but in the list of sequence we need values, we need number values. So to convert the time start and time end from the string to the number, it's very easy to use a new function that is Earth engine.number.parse, helping us to convert the string values to the number values. Earth engine.number.parse. There it is. Run the code again, and here we have a list of value for each year 2020 to 2024. But remember that our data limited to before 2024, meaning that we need to remove 2024 from the list of years. It is very simple technique to subtract the 2024 from the estimations. So that subtract 1. Run the code, and as you can see, when the list of year subtracted from value number 1, you will see that now we have 4 years, including 2020, 21, 22, 23. Great. In the next step, I need to make a function that collect or aggregate my data based on the months and years. It's very simple and easy to use technique. If you followed my tutorial in my YouTube page, I have already shown you how to use temporal collection function in this regard. But now, recently, I learned a new technique that is much simpler for the users and allowing you to make temporal aggregations for your studies. So, make a new variable. Here, we need to make monthly product. So, this is monthly NDVI equals to, we have a list of years. For each year, we want to have monthly data. From list of years dot map, make a loop using a function, each input year named as a year, and in the body the function returning the months inside of the year body, we need to define the months list. Return months again dot map. Here I'm making two different loop, one for layer and one for months, and here we are combining the months and years to produce a monthly product for during the year's period. Each input month named as a month here. Now in the new part or in the new body, we need to make a monthly collection. The monthly maximum value equals to, so the input image or the variable including all Sentinel-3 images is Sentinel-3 here. Copy and paste it, and then throw the calendar range earthengine.filter.calendar range. We need to add two different calendar range, one for year and one for month. So the first is based on year and the next will be for month. Again, dot filter earthengine.filter.calendar range, this time for months, input months, the field name is months, and finally we want to get the maximum value for each month. As this is a daily data, highly suffered from the cloud cover and the satellite noises. When you get the maximum NDVI, meaning that the low values or extreme low values and no data values created or coming from the satellite or coming from the cloudy sky will be removed in the monthly product, because most of these extreme non-values including the negative or low values, and as you know, the cloud cover highly reduces the value of NDVI per pixels. So when you get the maximum, almost you get rid of most of these problems in your NDVI image, and you can visualize the crop covers and vegetation covers in your image with a good quality. So the maximum image for each month is created, but we need the date of each image, or we need a new property for each input data as a actually system time starts. So a new variable as time equals to, using earthengine.date from year, month and day, we can make appropriate system time start for each available image in our collection. So instead of year, we have year, and months, we have months. Instead of day, just set 1 and remove the extra arguments here. Finally, the function returning the monthly max with the new property or the new time property. The new time property is system time start should be equal to the time dot millisecond. We need to have time information with the millisecond format. So here it is. Finally, as the output in this step produced in a list format. Let me show you the final result. Here, if I print the monthly NDVI in the right panel, you will see a list that is under computation, which has 4 elements, and each element including the images or monthly images. We have 4 years, now we have 4 elements. In each year or in each element, you can see we have 12 bands that's showing the monthly variation. Actually, this is the nested list, as you can see. The different lists separated from each other under a single list. If you want to convert the nested list into a single list, we need to use .flatten. So after flattening, again we have a new list here, but this time we have a single list with 48 elements. This is the single list. And now for the further analysis, we need to convert it from the list structure to the image collection structure. It's very easy. EarthEngine.image collection, open parenthesis opens and ends like this. Using EarthEngine.image collection, now I have one image collection with 48 elements. As you can see, shows the monthly NDVI with single properties related to the temporal information. So, for example, now I can, for example, for the geometry, I can select a new region in the croplands here, and then through the user interface chart, I can show you how the NDVI or the monthly NDVI values changing in the marked region as a geometry. Write print user interface chart image.series. Couple of arguments we have. Instead of image collection, we have monthly NDVI. Instead of a region, we have geometry, because for the marked region, marked point, or the geometry, we need to get the NDVI value. As the selected location is a point, the reducer should be reducer.first, the first value that is detected in the point location, reducer.first. And the scale should be, for example, 300 meter spatial resolution. And X properties, including the temporal information that is included under system time start property. Save your code, and also here you go. You can see the monthly NDVI variation with a high quality and lowest noises possible. So, and in the next step, maybe you need to have a look on the monthly image with the visual properties. Still, it is also very simple. Just you can use the previous codes which has been written. In the line 20, as you can see, we had Sentinel-3 median image, but this time I can visualize the monthly NDVI here, the monthly NDVI dot two bands that is stacked and through the dot two bands and clipped based on the region of interest. And here it is the Sentinel-3, the monthly values. Save your code and run the code again. In the task also you can see that the preview is saved, and then you can pick it up through the opening drive and open it up in the software. I will show you in the next steps. Here Sentinel-3 monthly is available, and now you can see the speed of processing increased, because instead of thousands of satellite data, we only have 400. We have 48 image, and visualization process that's highly speed up the visualization and the further processing in the EarthEngine platform. So this is the first NDVI image that you can see created. The lighter regions actually shows the croplands, and also the gray regions showing the rangelands, and the dark regions shows the water content or the soil. For example, I'm gonna select a time in the summer and then run the code apply visualization characteristic, and here we go. You can see that, but for some dates we may have some distortions and also some actually problems in our images that you can see in the some dates. They are highlighted in the output results. Maybe this kind of errors happens because of the some sort of problems or noises, and also sometimes maybe the spatial resolution is lower than the value we are expected. You can try it for the different dates, but the important thing is that the NDVI value for each month is actually cloud free, and also you can see the vegetation cover clearly for your region of interest. Maybe if you set 1000 as a spatial resolution, could be better for the visualization process when you are working with this kind of data. For small regions, maybe we have some sort of errors in estimations, but if you select a larger area, definitely you will get a better result, because this is a coarse spatial resolution product. You can see it is available, and we can use it for the time series analysis in the Google Earth Engine platform. So in the final step, I'm gonna show you the final result, a preview image we already created that is available in the Google Drive, and it is completely stored in my Google Drive, and after a few moments I will be directed into the folder. The Sentinel-3 output is available here, and now I'm waiting to go to the yes, here Sentinel-3 output is available. Through the right click, I can download the data and import it into the software. So let's see. Unfortunately, the speed of processing in my browser reduced a lot, and now in the home I'm trying to download the final result. Let me to do it manually. drive.google.com. Here I have Sentinel-3 output. Throw a right click, go to download. After a few moments, the data is downloaded. So as you can see, but this is a preview image, I can open it up in the QGIS software. QGIS is available here. This is the one of the examples that I have already shown you in the opening, and now I will remove it and open the new product. From the raster layers, browse into your system the Sentinel-3 data, the Sentinel-3 monthly, the Sentinel-3 output, and add it here. And as you can see, with 1000 meter spatial resolution, the output shows the vegetation cover, water, and the bare lands clearly. If you set the spatial resolution to 1000 meter, definitely you will have a better overview, or you will have a better visualization characteristic about your data. But if you zoom in a lot, definitely you will miss a lot of information because of coarse spatial resolution data that have. So I hope you liked this tutorial, and if you had any question or problem regarding this tutorial, you can reach me out through my YouTube channel, and you can put your comments and feedback in the video page, and the code is also available under the video description in a small box. And if you had any problem in the code, first compare yours with mine, and also if the problem still exists, you can reach me out in the YouTube channel in the comments parts. So thank you for your attention.